Hopefully you all now have a general understanding of how a database is designed. So once we've designed our database and stored a bunch of records in our relations, the next logical step is to start querying our database for useful information. The DBMS performs most of the heavy lifting for processing these queries, but how? So its first stop is the query parser, right over here, which converts the query into a format that is readable by the query optimizer, which uses information about how the database is stored to produce an execution plan for evaluating the query. And the plan executor right here is what actually evaluates the execution plan. An execution plan is usually represented as a tree of relational operators, which tells the DBMS the order in which it should select and filter data from the relations. Below that is the layer dealing with files and access methods. A file is defined as a collection of pages or records. Pages referring to chunks of memory, and records referring to single entries in a relation. Heap files, which are unordered files, as well as indexes, are also supported on this layer. The file and access methods layer sits on top of the buffer manager, right here, which brings pages in from disk to memory as needed during read requests. And below that is the disk manager, which, as you could probably guess, manages space on the disk itself. So at a high level, these are the constructs that enable a DBMS to process queries correctly and efficiently. But the industry expects more from a DBMS than query processing capacity. In reality, many people will be making queries at the same time, so the DBMS should have support for multiple concurrent users. At the same time, we want to give the impression to users that transactions are occurring synchronously, one after another, even if they're occurring simultaneously. Additionally, if the DBMS crashes for some reason, it should be able to restore itself in a consistent manner. And that's where these mechanisms, to the right, come into play. First off is the transaction manager. The transaction manager schedules the execution of transactions and ensures that transactions adhere to the DBMS's lock request and release protocol. The transaction manager works alongside the lock manager, which keeps track of requests for locks and issues locks when they become available. And when these locks are available depends on the locking protocol. So there's a couple of important terms here. First off, what is a transaction? A transaction is the execution of a user program that accesses or modifies the contents of a DBMS. Some examples of transactions are placing a reservation on a hotel website or accessing your checking account balance on your bank's mobile app. A locking protocol is a set of rules to be followed by each transaction to ensure that even though the actions of several transactions might be interleaved, the net effect is the same as executing all transactions in some serial order. If you don't know what interleaving is, take a look at this example. Here we have transactions A, B, and C. We want to fulfill all of these transactions, but we don't care about the order in which they're processed, right? As users, we really only care that they get done and that the data isn't corrupted. Our DBMS, which needs to process multiple transactions concurrently, might schedule the individual operations from A, B, and C out of order. As you can see here, the DBMS processes A1 first, but then carries out operations B1 and C1 before completing the remainder of A's operations. And then B and C take turns executing their operations until transactions B and C are finally fulfilled. So hopefully this gives you a better understanding about how interleaving works. Okay, so that was a bit of an aside. Let's get back to locking protocols. What does a locking protocol look like? An example protocol would be a system that has two types of locks. First one being a shared lock, second one being an exclusive lock. The protocol can issue multiple shared locks on the same object, meaning that multiple users can read the same piece of data at the same time, but this protocol may only issue a single exclusive lock per object. This means that if a user has the exclusive lock, no other users may modify that data until the original user has released the lock. The last piece of the puzzle is the log manager, or recovery manager. The log manager comes into play when we think about system crashes. When you have a system that's constantly processing transactions, there's bound to be a scenario where the system crashes in the middle of processing a transaction. When a crash like this occurs, what's the correct course of action? Well, a straightforward solution would be to revert the system's state to before that incomplete transaction was issued. Question is, how do we know what the system looked like at this point in time? Well, the log manager takes care of this issue. When a user issues a write operation to the DBMS, the log manager creates a log of that transaction before the DBMS fulfills the request. This technique is called write-ahead log, or WAL. When a transaction is completed, the log manager creates another log indicating this completion so the system knows which operations to restore in the event of a crash. A DBMS can reduce the time it takes to recover from a crash by periodically writing information to disk, effectively creating a checkpoint. Alright, so that's the anatomy of a database management system. Now that we have an understanding of a DBMS's inner workings, let's talk about the different people that are involved in using and maintaining a DBMS.